In this video, we're going to talk about existence and uniqueness proofs. So up until now, we focused on proving if-then statements, like if x is even, then x squared is even. And if you remember from when we were trying to think about how to quantify statements, another way of saying if x is even, then x squared is even is saying given any even number, that number's square is even. That if is really an implied for all quantifier. And then if you think about how we wrote our proof, we did that. We worked in general. We didn't pick a specific x. We didn't say, well, x equals 2 is even, and 2 squared is 4, and that's even. That's not a proof of this statement, because we're supposed to be proving about every even x, and that every even x's square is even. So we started off by choosing a generic even integer and writing down what that meant, and then giving an argument. And so today we're going to contrast that with existence proofs. So in our first example, we're asked to prove that there exist even integers a and b such that a plus b equals 10. So if you notice, we're asked to just prove something exists. We're not supposed to prove that it's true all the time, but just that it's true in an instance, right? There exists means that it's true at least once. So when we want to prove something exists, all we have to do is give an example. So here's a proof for example 1. We could just say consider, and then we just have to pick two integers, an a and a b, that work. So I'll choose a equals 2 and b equals 8. Then a and b are both definitely even integers, so they meet the conditions. And a plus b is 2 plus 8, which is 10. And we're done. We've proven that there exist even integers a and b such that a plus b equals 10 by giving an example. In our next example, we kind of combine the two kinds of proofs. We have an if-then statement, so we have that conditional statement, but we also have a there exists. So we want to prove that if a is a non-zero real number, then there exists a real number b such that a times b is equal to 1. So we have that if-then statement. We're going to do a direct proof, so we'll start off by letting a be a non-zero real number, right? We're going to assume the if, and then we're going to try to conclude the then. So we have let a be a non-zero real number. So then what is it that I'm trying to prove? Well, I want to prove the then, right? I want to prove that there exists a real number b such that a times b is equal to 0. And I'm proving there exists, so I just need to give an example. So I need to give an example of b that has this property, a times b is equal to 1, sorry. So then I need to figure out a b that makes a times b equal to 1. Now this statement is simple enough that I can probably guess what b is, but here's sort of a method that works even when you can't guess. So I'm going to start some super secret scratch work. Now this is super secret, so I don't show this to anybody. I'm not going to let anybody know that I've done it. It's on a scrap piece of paper that I'm going to burn and eat the ashes, because I'm going to do something bad, something that's not really good for proofwriting, but then when I write my proof, I'm going to take care and make sure that I prove things in the correct direction. Here's my bad thing. I just wrote down a times b is equal to 1. So I've really assumed what I want to prove. That's bad. The last line of my proof should be a times b equals 1. I shouldn't get to say that until the end. So that's why this is scratch work that I'm not going to show to anybody. But I'm going to pretend like what I want to be true is true, and then I'm going to solve for what I need, which is b. So I'll just divide both sides by a, and I get b equals 1 over a. And that's what I needed my scratch work for, to figure out the b that I was supposed to consider. So I wrote down what I wanted to prove. If I had known something about a, I would have subbed that in before I solved for b, but a was just a number, so I didn't have to sub that in before I solved for b, and then I just solved for b. And that tells me what b I get to consider. I'm going to consider b equals 1 over a, and then I show that he meets the criteria. So since a isn't 0, b is a real number, and when I take a times b, I get a times 1 over b, a times b, which is a times 1 over a, and that of course simplifies to 1. And I've proven what I wanted. I've shown that there exists a real number with the right property, because I found that real number. I solved for him, but I'm not going to show anybody that I solved for him. I'm just going to say, here's the b that works, and this is why. And that's the end of that proof. So in our next example, we're just going to extend the last example. So this says, prove that if a is a non-zero real number, then there exists a unique real number b such that a times b is equal to 1. So first we need to prove that it exists. So the first part of this proof is exactly the same as what we had before. So this is just the proof from before. And then the next thing we want to do is prove that that b that we found is unique. He's the only one that's going to work. 1 over a is the only choice that's going to work for a times b equals to 1. So to prove something's unique, we use a proof by contradiction. So we're going to suppose that it's not unique and then reach a contradiction. And it's so common to do uniqueness by proof by contradiction that we often don't say for sake of contradiction. We just start in. So I'm going to say, to see that b is unique, suppose that there's another one that works. So suppose that a z equals 1 for some other integer z. So I'm supposing it's not unique, right? That there's another z that works. And then I'm going to show that z wasn't actually different. So then ab is 1, but that's also az. And then if I can simplify, this means that ab equals az, and then I can cancel the a since a was non-zero. But then b is equal to z, which meant b was unique, right? Because there wasn't a different one. We thought there was a different one, but then we showed it was the same. So then we can say, and b was unique, and we're finished. So when we want to show that something's unique, we suppose that two things have that property, and then we prove that those two things are the same. In this case, we already had supposed that b had that property. We showed that it did. So now we're going to show that, suppose that z has the property, and then show that b has to be equal to z. So for our proof template, for there exists a unique x with a given property, first to show it exists, we give an example, right? We say consider x, and then we actually put in the blank a specific x that has the property that we're interested in. And then we show that x really does have that property. And then to show that it's unique, we suppose that x and z both have the property, and then show that x has to be equal to z, and therefore x was unique. And actually, you could do either one of these on its own, right? In our very first example, we just showed something existed, and that thing wasn't unique, and we weren't asked to prove that it was unique. So we just did the there exists part. And we might be told that something exists, and X just show that then it's unique, and then we would just do the unique part. So oftentimes we see there exists a unique together, but we could do each part separately. In this video, we discussed existence proofs and discussed uniqueness proofs, and we gave an example of each, and then we concluded with a proof template for there exists a unique proofs, and mentioned that we could do either there exists or something's unique, or prove that something exists and is also unique.